Welcome back to this course on Fundamentals of Computer Architecture. In this module I will explain the MIPS64 instruction set architecture, or ISA. The MIPS64 ISA will be used for code examples throughout this specialization. This lesson will highlight some features of MIPS64. The goal of this module is to enable you to first describe the main features of the MIPS64 instruction set architecture, or ISA. Second, to translate small pieces of usually C code to MIPS64 assembly. All our examples are in C, but it's a small step to translate to other procedural languages. And third, to optimize MIPS64 code using compiler techniques such as elimination of induction variables and loop unrolling. This lesson is based on Appendix A and K of the 5th edition of the textbook, Computer Architecture, Quantitative Approach by John Hennessy and David Patterson. It's also based on the manual, the MIPS64 instruction set by MIPS Technologies Incorporated. Since MIPS Technologies has been acquired by Imagination Technologies in 2013, if you go to the website mips.com, you will end up on the website of Imagination, but there is still a lot of information about MIPS processes there. Here I present some highlights of the MIPS64 instruction set. First, it's a simple load-store instruction set. That means that only load and store instructions access memory, and to process data stored in memory, you need to load it into a register first. Second, it is designed for pipelining efficiency. For example, the source registers are always in the same place in the instruction set encoding. This allows to read the source registers before the instruction is decoded, and we know what the instruction should do. Finally, it's a very efficient instruction set for the compiler to target, because in most cases it can be well predicted how much time a sequence of instructions will take. A few words about the MIPS64 registers. MIPS64 has 32 64-bit fixed point general purpose registers, abbreviated as GPRs. So each register is 64 bits wide and there are 32 of them, R0, R1 to R31. R0 is special because it's a hardwired 0. It always holds the value 0. You can try to write another value to it, but it will always stay 0. MIPS also has 32 64-bit floating point registers, FPRs. These floating point registers can hold a 32-bit single precision floating point or a 64-bit double precision floating point. You probably know the keywords float and double from the C programming language, and these correspond exactly to these data types. When single precision is stored within one of the FPRs, then only half of these floating point registers is used. MIPS also has a few special registers. In particular, there's an issue because the product of two n-bit registers is a 2 n-bit number, which does not fit in an n-bit registers. There are several possible solutions for this, but the solution chosen in MIPS is to have two special registers called high and low. The low order bits of the product are placed in the low registers and the high order bits in the high register. Thereafter, the low and high registers can be copied to the general purpose registers for further processing. Other examples of special registers in the MIPS ISA are which holds the outcome of floating point comparison instructions, and the exception program counter, which holds the program counter or instruction address of the instruction that has caused an exception during execution. MIPS also supports several kinds of data types. The integer or fixed point data types are 8-bit bytes. In C and Java, for example, you allocate a byte using the keyword char. MIPS also supports 16-bit half words, for which in C and Java you usually use the keyword short. Well, in fact, C is not very precise about the size of its basic data types, but in Java, a short is always 16-bit. The next basic data type supported by MIPS is 32-bit words. Notice that a word is not always 32 bits long in computer architecture. In MIPS it is, but in Intel a word is 16-bit. Finally, and this is different from the MIPS32 architecture that you might know, MIPS64 also supports 64-bit so-called double words. In fact, this is the 64 what gives MIPS64 its name. The main reason to switch from 32-bit to 64-bit is to increase the amount of directly addressable memory. It is important to realize that arithmetic operations process 64-bit registers. Data types smaller than 64-bit are either 0 extended or sign extended when they are loaded into a register. For example, when a byte is loaded using the load byte unsigned or LBU instruction, the byte is 0 extended, meaning that the free bit positions are filled with zeros, meaning in turn that the byte is interpreted as an integer number. On the other hand, when a byte is loaded using the load byte or LB instruction, it is sign extended, meaning that the sign bit, which is the most significant bit, is copied into the free bit positions. Copying the sign bit essentially means that an 8-bit 2's complement number is converted to a 64-bit 2's complement number, and that is exactly what we want. Finally, for this slide, MIPS also supports 32-bit single precision floating points, as I said before, floats in C, and 64-bit double precision, which are called doubles in C. This completes this lesson. Thanks for watching. In the next lesson I will describe the MIPS64 addressing modes and instruction formats. Stay tuned.